Okay, thank you very much. It's a pleasure to be talking to you, to all of you. And yeah, the purpose of my talk is a little bit giving you a flavor of this field of positivity bounds that has been blooming in the last years. Okay, of course, it's a very old topic that people use it in the old days, but probably in the last years becoming more important because we have techniques, numerical techniques that allows to really take these positivity bounds as a whole set of constraints into theories and get interesting results. Okay, so it's kind of putting all together. Probably in the old days, people were taking one or two bound of these because it was complicated to put all of them together. So the idea is today, okay, of the last years, is that okay, we can deal with all of them, put them together, and see the consequences of them. And now it's interesting to bound theories that we cannot do because we don't have a Lagrangian for them. Okay, so and concerning these theories, I'm interested is large chain theories, in particular large chain QCD. Okay. So the motivation for me is a little bit, if you heard my CV described nicely before, is a motivation to understand strongly coupled theories. Okay, not only because they play, we know, important role in nature. Okay, we know QCD is strongly coupled, and we cannot, even we have the Lagrangian, we cannot have we have little predictions. Okay, so sometimes we have the theory, but we don't know how to calculate things, and this is the case of QCD. But my motivation is a little bit always going to beyond. Okay, I want to understand about the strong theories because I want to apply beyond the standard model. Okay, so we heard about composite Higgs. This is an options. Open options that is tested at the LHC, so it's an interesting possibility. But again, we cannot we can describe it qualitatively, but we don't have precise calculation, because if it's strongly coupled, the Higgs composite is a strongly coupled theory, which we cannot calculate in a consistent way. And also for dark matter, of course, we don't know what is dark matter, so dark matter could be again coming from some strong sector. And we want to get prediction out of it. And again, we find ourselves in the same situations, okay? So even that is very difficult to get analytical results from strongly coupled theories, it is very important, at least, I think, to me, to find limits at which things simplify, okay? So it's the usual thing, okay? We don't understand a theory, but in certain limits, at least we can calculate things, and approaching in different limits, we can get a better understanding of the theory. And there are beautiful examples. The one I will talk about is when you take number of colors of some SUN strongly coupled theories, okay, taking this number of colors to infinity, okay, taking large n limit, okay, as we will describe this afterwards. The theory simplifies a lot and allows us a weakly coupled description of it, okay. Another example is, of course, holography, okay, has been a very useful tool to learn about strongly coupled conformal field theories in 4 dimensions by going to the dual holographic picture of it. That is a theory living in ADS, anti-de Sitter, in a extra dimension, okay. So it's again a relation between strongly coupled theories and weakly coupled theories, and of course both of them are related because, I mean, this holography works the best when you are dealing with the large n limit of this conformal field theory. Okay, so now positivity bounds can help onto these theories. Okay, we have these limits, but as we will see now, we cannot get, even in this simplified limits, we cannot get much information. So positivity bounds can help us to understand these particular examples much better. So let me start with the example I want to discuss. As I said, I'm interested in strongly coupled theories. I cannot do much of it, but I can take the large n limit, and as shown by the beautiful paper of Toft and elaborated by Witten, amplitudes simplify extremely in this limit, okay, because these amplitudes become amplitudes are mediated by weakly coupled colorless states, what we call mesons. Okay, if you look at any diagram in the planar limit, okay, that is the large n limit, you can see when you cut, you will see the particle that is mediated is always one single colorless state. It's never 2 colorless states, only one. So you can describe this amplitude as mediated by a colorless state that we call a meson, okay? So in this limit, I can say that QCD is described by a theory where the mediation of the amplitude is just this single meson. But not only that, I can say that the coupling, you can get the scaling of the coupling to go like 1 over the square root of n colors. So when n colors go to infinity, the coupling goes to 0. Okay. So in this formal limit that I will be taking, of course, n colors going to infinity, so the coupling going to 0. The theory simplifies because, of course, it's a Willy couple theory, and we can do perturbation theory. Okay, so we don't have to include loops. Okay, and on 3 level is a good approximation, at least the leading order approximation as we do in perturbation theory. Okay, so the interesting thing of this limit is, instead of talking about quarks and gluon in a SUN color theory, when we take this limit of color to infinity, the theory goes from a strongly coupled theory here to a weakly coupled theory. But of course, my states are not anymore quark and gluon, but meson, QQ bar states, or gluon states, glue balls. Or if you want, also there are baryons that are racing from a solitonic state of the meson. Okay, so we can forget by baryons that are solitons, and consider only that do not appear in the amplitude, but consider only the meson state. That in this case I would be interested in a state that are QQ bar. Okay. Now this is very interesting. Okay, now I have a weakly coupled description, but of course, even it is a very powerful simplification, it's still difficult to get predictions, because of course this is a theory of infinite meson. In fact, it can be proven that you need infinite of them, because it was already explained in the paper of Witten. To get things that we know that go logarithmically at high energy, we know that the coupling is small, and things have to go logarithmically. This implies that I need infinite mesons. Okay, and of different spin. And it, of course, when you have infinite meson, it means that you have to know the couplings. You want to write a Lagrangian for them, and you need infinite couplings to describe the Lagrangian, infinite masses. Okay, so it looks like, oh, it's nice, it's weakly coupled, but you have infinite parameters, so you cannot get prediction is 0 when you have infinite parameters, no? Okay, so still, we need another handle to understand how to deal with this infinite number of states. Even that a priori you could write a Lagrangian with all of them. Okay. Now let me say that this fact that we have infinite meson, we see it in QCD. Okay, you open the PDG and you find states or resonances. We call it resonance because, of course, QCD is not in the number of colors infinite. This number of colors is 3, but looks like it's relatively a good approximation, because we see kind of resonances, or at least something that are width over mass is a little bit smaller than 1. Okay, of course, 1/3, something like this. Okay, that's not much, but at least we can help us to understand, at least in this limit of n colors going to infinity, that seems not to be far away from what we observe. Okay, we observe a bunch of resonance of all spin in QCD, and with width small enough to talk about resonances, okay, about the states, particles, okay. Now, so I was saying this is not, I mean, this is very simplified assumption, but difficult still to get predictions, okay. Now where it comes the idea of positivity bounds that I was saying have been flourishing in the last years, okay. By here, I just put probably one of the first papers of this second era of using these constraints, these positivity bounds to get information about theories, okay, because there is a lot, of course, papers before this, as I will explain to you. This is based in simple things of quantum field theories that we have been using all the time, so probably you used it previously. So and it's only, I'm trying to say, recently that we have seen trying to go beyond, okay, with these things, and to get really down to constraining theories, okay. And this positivity bounds, as I said, this is basic idea, you know it, everybody know it. It's kind of generalization of the based on the generalization of the optical theorem that we all know, and you can find in the textbooks, okay, that in the forward limit, the elastic scattering, the imaginary part of elastic scattering can be written as the two states going to some intermediate state, F, and back to this state. Okay, so you see that this is an amplitude, an absolute value square, that must be positive. Okay, so is this positivity here? What I'm talking about positivity bounds, kind of. Okay, but not only this one that is in the forward limit, but I will see that there is more. Okay, even when you go beyond the forward limit. Okay, this is the point. Right? This is well known, but you get one bound here, and we want to go beyond this point. But this kind of, the idea is similar. Okay, it's only kind of generalization. In fact, this simplifies already a lot when I go to large n, because as I said, a large n is like a weakly coupled theory. So what it means is that theory at 3 level. Okay, I don't have to do loops. I have a theory at 3 level. The only complication is the particles mediating the amplitude are infinite of them. Okay, with infinite couplings, infinite masses. Okay, that's the only complication. But a priori, you can draw that 3-level diagrams for everything I want to say. And in amplitude AB going to AB will be mediated in channel, T channel, U channel. Of course, here I'm only putting the channel, will be mediated by interchange of a single state. And of course, I look at the imaginary part, is putting this particle on shell, and this becomes just this coupling square, okay, that modulus square, that we know, of course, is positive. So in some sense here, the positivity bound is just trivial. It's telling me that the imaginary part depends on this square of couplings, that of course, modulus square of coupling, that of course is just positive. Okay, you don't have to know much about optical theorem, just you see that this is a positive quantity. So in our case, it's much simplifying, because we're dealing with the level theory. Please interrupt me anytime, okay? I'm very simplistic at the beginning, okay? But you can stop me anytime. Now, we want to apply this thing to large and QCD, so I will describe a little bit the idea of how these bounds are constructed, and later on to get the implications, okay? The full implication of this thing. I'm saying little implication here that have been considered before. Okay, here we're dealing with the full thing. Okay, that's what makes probably a step forward from the old days. Okay, so let me do here a similar thing, but the first thing I want to understand is the analytical structure of the amplitudes in the latency limit. And as I was saying, the latency limit, this is mediated by single particles. So the analytic structure of an amplitude. Okay, if I go to the complex plane, I do an extension in the complex plane, and I fix U, or I fix T, the other one. Okay, and I look at the plane analytic structure in this complex plane. I fix, in this case, U. Later, I can also fix T. I know that the only singular points are at the real S. Okay, corresponding to the poles of the exchange of particles as at the level. Okay, so these are simple poles, okay, that are located which the masses of the particles are. Okay, that can have a positive S. Okay, but I can also have, of course, interchanging particles in the T channel. Okay, if U is fixed, okay, S is minus T minus U, minus 4m squared for the mass of the particles that are and describing this amplitude. Okay, so in this case, I have also, if I have poles in T, I will see it as a negative poles in S. Okay, so the analytic structure, I have poles in the positive S corresponding to the poles in the channel, and poles in the negative S corresponding to the T channel exchange of particles. Okay, and these are simple poles I can have. Okay, this for an amplitude of whatever particles. Now I'm not considering, we'll go to pions, okay, in particular pion scattering, as we'll see later, and we consider massless states. In the case that the external states are massless, this M is the external state, this goes to 0. And something I want to say is, of course, these poles start at some M, I will call capital M, the first one, okay, and I'm assuming this is discretized. And I am assuming also there is no massless state, okay? Although the pions are massless state, but the pions do not enter in the pion scattering, okay? But that's are minor things, because I can change it, okay? If there are poles here, it will be poles here, and that's not a problem, okay? You just have, I mean, you put whatever you find it, and you go on, okay? So I'm saying this is, I mean, foreseeing my simplifying assumption that I will be using when I go to pion scattering, in which there is no, the amplitude is not mediated by pions, mediated by heavy guys, okay? Okay, now
Can I ask a question, Alex, before you
yes.
move on? Hi, good to see you. So what my question is, is the branching cost singularity 1 over n suppressed in this picture?
Yeah, exactly. Yes. So a priori,
Okay.
I could go on in my expansion at the level. I could do loops. This is 1 over n expansion, and now yes, I'll have it will have in the imaginary part on the real S. I will have branch cuts and all these things. Yes.
Oh, okay,
So,
got it. Cool.
yes,
Thanks.
exactly. I could go on, and now this is something beyond, of course, to how to catch these things, and could be problematic, of course, if you can change from simple pole to branch cuts. Yes, indeed.
Thanks.
Okay, thank you. Now the dispersion relations I want to get, or the relation I want to get, will be based in this whatever amplitude divided by S to some k plus 1. Okay, where k will fix to be 1, 2, 3, 4, whatever. Okay, any power of k. That of course this will bring out some singularities here when S goes to 0, because I'm dividing by S with some power. Okay, I will put here in green to differentiate from the other ones. So associated because I'm taking instead of m the amplitude that has no singularity at S going to 0 by S over k plus 1, and k can be any. I mean, we will discuss about it, but in principle it could be 0, 1, 2, 3, 4, any integer number. Okay, yes, now the dispersion relation, I mean, this is well known. I mean, trick that you have done many times is to go to the Cauchy, use the Cauchy theorem, okay, and based on the following, okay, take a contour at infinity that is very large, and if S going to infinity, the amplitude m over S to the k goes to 0, okay, of course, for some k, this will always happen, okay, at least for k equal 2, for example, we have the Froissart bounds, this will go to 0, so at least k equal 2, you're guaranteed that this will go to 0. It means that the integral will be 0, okay, for certain case, okay, but for sure k at least 2. And now I can deform, or you can use the Cauchy theorem the same, or deform the contour and around the poles, and around the simple poles. And now tell me that the integral over the sum over residues, so the Cauchy theorem tell me that this is the sum over residues, it has to be 0, or equivalently the residue of the origin, okay, that has an origin coming from because I took m over S to k plus 1, plus the residues at the pole, okay, of the particles that I'm exchanging in my amplitude should be summing to 0. Okay, so in some sense I'm getting a relation between this residue and the other residues that are of different origin. The residue at the origin is telling me about when S goes to 0. Okay, the residue is when I is going to 0, so it's telling me about the low energy expansion of this M. Okay, so telling me about low energy effective field theories. Okay, so the low energy, I can always have a low energy and effective field theory of the pions, what is called the chiral. For example, if I talk about pions or another theory, what I call the chiral Lagrangian. So in some sense, this thing of the origin is telling me about the chiral Lagrangian of the low energy effective field theory parameters. Okay, and in relating this with things that are physical, okay, like masses, and residues means couplings. Okay, so I have a relation between low energy effective field parameters and the masses of the mesons that are the exchange particles, and I'll put it more precise later, okay, but you can see the flavor of the idea that you have this relation between low energy effective field theory and things and parameters of the theory that are masses and couplings that, as I said, we don't know from large chain. Large chain doesn't tell you, only tell you there's a weakly coupled theory, doesn't tell you about masses and couplings, okay.
Sorry, here's another question, sorry. Just to get a sense where you're actually heading with this. So in order to actually determine k, don't you have to have some sense of analytic properties of m, the amplitude mst? So I'm just trying to understand the context in which you apply this machineries. So yes, I understand that you can take large enough k such that this is always convergent, and just therefore you can apply the Cauchy. But in practice, operationally, don't you have to have some idea about the m of st, at least some limiting behavior of this amplitude as a limit of s, in order to even determine what k you need to use?
Oh yeah. Yes. This will be what is the k I have to put here. I'm saying will depend on the amplitude. I'll take k equal 1, k equal 2. I can take, I am saying k equal 2 is already, you can prove it, this goes to 0, but k equal 1 will depend on some assumptions on the amplitude, yes.
Oh,
or you
okay,
could take k, k equals 0, you could take k equals 0 if you say, of course, the amplitude goes to 0 to infinity, but this is, of course, this is a strong assumption, and it could be not true, yes. So depending, yeah, if you knew a little bit about the analytics, I mean, of the function, how the function behaves at infinity, at a large, at fixed, in this case, u, okay, that will help a lot, okay? That's an information that you need, of course, to use, okay?
Right,
Yeah.
okay, thanks.
Sorry, I have also a question. Oh, can you hear me? So how can you ensure that all the poles are simple on the SS6?
I can assure it in the sense I was saying before. This is a large. I'm assuming this is a large n theory. Okay, so in the formal n color going to infinity. Okay, the large n tells you, as I was saying here, that this coupling goes 1 over square root of n, so the coupling goes to 0. Okay, of course, if I take the exact limit is 0, everything is 0, couplings are 0. It's a weakly couple, is a free theory. Okay, but so this is what I'm saying. I'm taking this formal limit in the sense I'm approaching an epsilon away from 0. Okay, I'm approaching this limit. All the time I'm thinking that n goes to infinity, of course, but not taking it explicitly. I mean, okay, taking this formal limit, I'm saying. So if we take this formal limit, I only have 3-level particle exchange.
In your numerical things in the later, are you really taking n to a large number, or just take it as a 3?
No. I'm taking always n to infinity. I'm taking always everything I'll say is the large n limit. The leading, okay, you can say this is the leading contribution at, okay, of the large n theory. Okay, it's like, I don't know, you have a weakly couple theory, you calculate 3-level. This is the leading contribution. After that, you can add loops. You could add loops and now see how things change. Okay, you could add, but as we were saying before, now we have loops. When you cut, the imaginary part will give you this branch cut and all these things, and people have been considering things like this, okay, with positivity bounds. Okay, you appear branch cut, but still you can say things are deformed, and okay, so there is people taking not only, I'm taking simplified assumption because you see my point is we don't know much still. We don't know, even that the large n theories are very useful as a limit. We don't know much, okay, and the point to me, my motivation is, okay, let me get this limit clear. If I can get more information on this limit, and later on, of course, I know number of colors infinity is just not realistic, okay. But at least I have this limit. I understand the theory and this limit, as we do with perturbation theory, okay, all the time. Okay, let me calculate things at the level. Now I see the scattering is this, and now I put deformation. I mean correction to these things that are loops. Okay, so I want to understand the theory in this limit because we don't understand it. The only thing we know is that there's a weakly couple theory, or even a free theory if you want. And my intention is really taking this limit, infinity, and later on, and compare a little bit with QCD. Yes, I'll do a little bit of comparison with QCD. Okay, but for example, also with lattice QCD, people in lattice are taking trying to take number of colors infinity, or extrapolate to number of colors infinity, so you can do some comparison, or can be useful, these two approaches. Okay, but no, I will not fix it.
Do you have some idea about the real QCD? I mean, whether you can well approximate with the 3-level exchange, or you have to include the continuum things?
This is very difficult. Number of colors in QCD is 3. So,
okay.
So yeah. So your expansion parameter 1/3 is not very good. So you would expect 30%. Surprisingly, large n, the limit with the prediction for large n QCD, okay, there are a few predictions. For example, you have weakly coupled states, so resonances with the width is smaller. More or less, this is what we observe, and there are more of them. For example, you expect that the singlet and the triplet in the have equal mass, and we have this prediction like the W mass, the omega mass in QCD similar to the rho mass. Some prediction of QCD. Sorry, some prediction of large n, we see them in QCD. Yeah, there is, I mean, but I don't want to enter into this thing. I'll discuss a little bit later on, okay?
Thank you.
Because yes, indeed, at the end of the day, we don't want to take this in infinity, yeah. Sorry. Okay, so now this approach can be used whenever any amplitude. I'll do it following a little bit the steps of Albert and Rastelli that they started doing for pion-pion scattering, and I want to go a little bit beyond what they did, and this is what I forgot about to say that this talk is based on my work that I mentioned at the beginning with my students and Francesco Riva. Okay. Now, so I'll not consider just a simplifying theory of QC with two flavors. Okay, of course it can be generalized. It's just not to mess up with many numbers here. So I will consider this is an SU2 global symmetry. So I have, okay, in QCD, if I have two flavors, I'll have SU2 left cross SU2 right broken to the diagonal subgroup. That will be isospin. Okay, so here in the mesonic, I'm talking about meson because in large N I don't see quarks, I don't see gluon. I have mesons only in my theory, are the fundamental states. Okay, elementary particles are, okay, my mesons in this limit. Okay, and now these guys, the pions, will be triplets. Okay, of course, are the Goldstone coming from these global symmetries, but I don't really need to say much about the Goldstone properties here. Only that I consider they are massless. Okay, no, they are Goldstone, so they are massless, but I will not use anything else. Okay, and they form a triplet of this SU2 global symmetry that is isospin. Okay, so I'll consider these two, the scattering of two pions to two pions of different flavor. Okay, and it will be useful to use the composition in isospin. Okay, and what does it mean? Why I'm doing this? Because it's because there is an extra condition when you go to large n number of colors, is that the meson are QQ bar states. They're not QQ bar, okay, are not theta quarks, are QQ bar state in this limit. So we know that the meson's isospin has to be the product of the isospin of the quarks, that is, it are doublets, okay? So the isospin of the meson can only be 0 and 1, cannot be 2, okay? In principle, the intermediate state of a pion are triplets, so it could be isospin, the intermediate state can be isospin 0, 1, and 2, okay? Okay, because this is, but I know in large N, these guys cannot be there, okay? So in general, I'm saying there's 3 guys, but now in this limit, there is an extra important thing, because tell me that there is not those state of isospin 2. What does it mean is that when I look at the pion scattering and I put them in a isospin state equal to, okay, I know that when looking at this amplitude, when these guys are in isospin 2, cannot have poles in the H channel, okay, because there is no state isospin 2. Okay, so here is channel pion going to some particle here, mediating it here, cannot be there in large N QCD. Okay, that's important because again, give me information of the analytical structure. There is no simple poles if I'm looking to this amplitude. Cannot be simple poles in the real S, okay, because large N tells me there is no mesons with these quantum numbers, okay? And I'll do it slightly different. The amplitude I'm taking is because the paper I did this, but you could use this amplitude, this one, but I'll use it, I'll use it slightly different. I will consider the amplitude isospin 2 in the T channel, okay? So we're considering that these guys are in the isospin 2 state, okay? So what it means that it cannot be poles in the T channels, okay? So I could use the previous one, but I'll use this one, at which, of course, by the same argument, I can say that there cannot be states here in the T channel because in large N I don't have isospin 2 states, okay? So I'm saying working with this amplitude, isospin 2 in the T channel, that is a function of S and U, and can be showing that is crossing symmetric with S and U. Okay, now as I was saying, the analytic structure simplifies because there is no now only poles. There's no poles in the T channel. So when I look at this amplitude divided again by this SK plus 1 in the complex S plane, it can only be apart from the ones coming from, because I divide by S to the K plus 1, apart from the poles here, can only be poles in the S, real S, okay? Okay, but not in the negative S, because the negative S, as I was saying before, are coming from the T channel. And in the T channel, I mean, in this case, in this amplitude, I cannot have particles because will correspond to isospin 2 states. Okay, so this simplifies okay, the singularities of the amplitudes. Okay, again, I'm taking this at u fixed, and I'll be taking u fixed going to 0. And now I do the same thing. I do the Cauchy at infinity that is related with the, okay, I'm taking this amplitude at infinity, take the contour that can deform it to be, I mean, the same say before, okay? And now I get a relation between the sum of residues has to be 0, or written in this way, the residue here, it can be related with the residues of the poles of you interchange the meson states. Okay, so I'm simply telling me the residues of the at 0, okay, of this thing are related with the residues here that I can write, of course, until level. This is the residues of the, when I am sitting on the exchanging state, this is the coupling square absolute value, okay, divided by the mass, because the amplitude I'm considering has an S, okay, so S on shell goes to the mass of the particle, to K plus, and now I can do a partial wave expansion, okay, such that I can decompose the sum over the different spins of the states, okay, so, and here appear, depending on the spin of the state that I have here exchanging, or the channel, or I have here I am sitting on the pole of this particle, it will appear the Legendre polynomial, okay, and tells me exactly what is dependent on U. Okay, U is fixed going to 0. Okay, I could take exactly to 0, but the point here is not taking it, it's doing expansion in U. Okay, to get more things. Okay, this is what I was saying, to go beyond previous studies. I'm going to take U going to 0, but then a Taylor expansion of it. Okay, but I know the dependence just by partial wave expansion has to be the U dependence on this side is known. Now back to the residues here. This is the expression. I have to look at this is the residue of this. I have to look at S going to 0, of the amplitude with S going to 0 to get the residue. Okay, and of course, this is this amplitude when S and also U goes to 0 has an expansion in powers of S and U. Okay, and these coefficients that I will call G10, G20 are related with the Wilson coefficient of the Caille-Lagrangian. Okay, so this is the lower, what I was saying, this is a relation between the low energy effective field theory, okay, parameters, okay, that are, okay, I can describe for the pions an effective field theory pion. This is well known, it's called the Caille-Lagrangian, and I have coefficients, the Wilson coefficient, that I don't know what they are, and they are related, of course, with these G's are here. Okay, I will tell you later more into connection with if you are familiar more with the Caille-Lagrange, I will tell you more the exact connection. Okay, but you can see that this, you're taking the amplitude going to with momentum to 0. It's obvious that these G's have to be related with the Caille-Lagrangian. Okay, so there's a relation between the G's and the couplings and masses summing over all of them here, infinite states. So the same particle has to go from 0 to infinity. Okay, so this is all the way down there. Okay, and important, as I was saying, that there is a crossing symmetric thing, okay, that of the amplitude, okay, and will tell me a lot of this. Okay, so let me look. Okay.
So right now you are looking at the amplitude with the isospin 2, but if you look at the amplitude with the isospin 0 or 1, you don't get any non-trivial things here. So here is crucial to have a amplitude with the isospin 2. Is it?
No. If you take the other ones, you will get also information. Here you will get also information here, but you get here more information because so now we can. Yeah, here if you don't here I can use the fact that last chain tells me that there should not be poles here.
Okay.
Okay. So this is much more information. In the other ones, if I take isospin 2, I will have also poles here. I can do the same thing. Okay, but I have poles here in negative S corresponding to the T-channel exchange. Okay, I can have, okay, for U fixed, of course, U fixed, I don't have poles in U because U is fixed, so I can only have poles in S and T. Poles in S comes here, and poles, and the poles in T come here, as I was saying, because S equal to minus T minus U, okay, the massless pions case. Okay, so yes, you have, but no, you're missing, this is important here because you have more information because here there is no body. Okay, and now this gives you some positivity. I will talk now. Will some positivity extra positivity constraint that probably you don't have them here when you use it in some other amplitudes. Okay.
Okay, thanks.
Okay. Okay. So let me go to the detail a
sorry.
little bit.
I also have
Sorry.
a question.
Yes.
Is there any reason why you look at only the S complex plane, not the TU?
No. There is no reason. And indeed, I mean, you mean S or T plane? Yeah. I will. Yeah. I want to get everything. Exactly. So I want to get everything, not missing any piece of information with this expression relation, because the idea is to put everything. Okay. Exactly. So I have to look at this plane, T plane, U fixed, T fixed, everything. Okay. At the end of the day, there are not many independent ones. Okay. So at the end of the day, there are two independent ones because, okay, I'm missing a little bit because if you go back to the pion scattering here, with one of these, I mean, these are related. The isospin 2 relative to isospin 1. There are some relations here, okay, because I have a lot of crossing. At the end of the day, you are doing pion, going to pion. So the exchange, these are the same particles, so there's a lot of crossing and give me these constraints. So crossing give me a lot of constraints. Okay, so at the end of the day, you're right. Okay, I have to look at everything, not miss anything. But if I have more time, I will tell you there is only, I can talk about this amplitude in the S, always in the S plane. For U fixed and T fixed, two things. Okay, these are the rest of the amplitude looking at other channels and other planes are can be put it as a I mean, that do not give me independent constraints. Okay, so I'm saying yes, I have to look at everything. Bottom line, at the end of the day, looking at two dispersion relation is enough. Okay. And that will be considered S plane and U fixed and T fixed. That's it. Okay, because I'm saying this is because pion is simple in the sense I have crossing and all these things. And I'm skipping a little bit these details, mathematical details, okay, because I'm putting already some already details for the other rest. Okay. Yes, thank you. Okay, so let me do so how it will look like with this expansion. As I say, they do the Taylor expansion here. Okay, and a Taylor expansion here is easy. It's a Taylor expansion of the Legendre polynomial, and the expansion here, of course, you see here there is U's, okay, U square and things like that, and we'll as when I look at the residues here, depending of the K, we'll select different couplings. Sorry, different Wilson coefficient, different G's, okay, that they determine my low energy expansion of the amplitude. So here is for K equal 1, I have exactly this. G10, G21 of U square, okay, so an expansion in U on the left-hand side coming from the residues at S going to 0, and on the other side I have the coupling, the information about the residues on the top on shell of the different states, so I have to sum over all of them. The coupling is squared again, and now it's a Taylor expansion, if you can see, of the Legendre polynomial, okay, and appear over, because the expansion in U over the mass square, okay, appear in this way. Okay, now what is the key point? Usually in the past you take the first one, okay, in the expansion you take U equals 0, that is equivalent to T0. Yeah, sorry, here I fixing first U and after that T. That is usually the T0 is the forward limit, that is the usual one. Okay, so sorry for here I'm using U from the beginning because the paper was in this way, but it's equivalent kind of. If you are taking this, this is not the forward limit, this is a kind of backward limit, but it's equivalent to taking the T channel T forward, the forward limit of another amplitude. I'm taking some amplitude of which the simplicity comes from the U going to 0. Okay, and this is what I'm trying to say. This is usually what people consider in the first one, U0. Okay, so only the relation between U, when you take U0, okay, you have the relation between the leading, okay, the leading expansion in the leading term in the expansion at the momentum 0 of the amplitude with sum of coupling over masses. Okay, but I have more relations. Okay, if I do K other case and I have this U expansion. Okay, so now I have in this expansion for K1, K2, K3. Now I can relate this coefficient, okay, with the coefficient here, the coefficient in front of U with the coefficient in front of U here, and that's it, okay? And in particular, I get now the contribution of this G10, okay, or G10, T20, G20, G30, Gn0 in general is equal to the first term, okay? Now the Legendre polynomial Ag1 is 1, okay? So I get 1 over the mass square, the coupling square. For the G10, for the G20, I get over M4. For G30, I get M6. So I get this kind of prediction, okay? The Wilson, this coefficient of my expansion of the amplitude at zero momentum will be related with Wilson coefficients of the chiral Lagrangian. It's a very simple thing. It's the coupling square divided by the mass square. Okay, why is important? Because this is positive. Okay, so there's a contribution of all meson, but it's positive. All are additive. Okay, all contributions are additive. Cannot be cancellation. Okay, so it's clear if I have infinite, and it has to give me a result that is not infinite, the coupling must go to zero. It's already telling me a lot. The couplings for higher spin, this is large n doesn't tell me anything. How the coupling to pions at the large mass goes. Okay, here it's telling me of large spin, that if I have infinite states, okay, at some point the coupling have to go to zero. Okay, otherwise I will not have convergence to a some coefficient of the Wilson coefficient. Okay, and it gives me, okay, this is for this thing, but I can relate also other coefficients as a function of something, and you can see, because these derivatives are also, you see here, there's more positivity I was saying. It's not only this is positive, the first derivative Ag1, okay, in the stellar expansion of the Legendre are also positive. Okay, and these are positivity that I see here. When I look at other, like G21 related with this one, because P prime J at 1 is positive, I also get some relation of positive quantities. Okay, again, for any, you can show for any Wilson coefficient that's important, the contribution of all meson are always additive. Okay, they appear additively to the Wilson coefficients. Okay, and again, it should be a convergence, and that tells me that that this coupling must be smaller because there are infinite of them. It cannot be growing.
Hi, Alex.
Yes.
I'm just curious. The way this Wilson coefficient appears is like you basically have a three level exchange of mesons, either spin 0 or spin. Then you just integrate out, and then you have basically G squared over M squared times momentum squared over M squared expansion. And this is Gn of 0 looks like taking exactly that form. And also probably if I do the same exercise with a spinned intermediate state, I might get the second line. Have you thought about that thing? You know,
no, yeah, it looks like this, but you see, rigorously, you cannot derive like this. Intuitively, I think what you're telling me, oh, intuitively, yes, it looks like this. Yes, you're right. I don't know if you're telling me this. Intuitively, you are right. Oh, yes, okay. I take momentum 0. We know how to integrate a particle. It comes the mass. Yeah. We know. Okay, coupling square over mass square. That's it. Yes, right. You are right. But tell me what is the exactly amplitude when I mediate a spin 25. You see, I don't know exact amplitude of the mediation of spin 25. I cannot tell you so. I don't know the theory. Okay, now, so this is what I'm trying to say. It could be that in the numerator, I have S or T's or U's. Okay, when I do the low energy expansion, they don't appear here. So it's true that intuitively, oh yeah, it smells okay. Yes, of course, you integrate a particle, coupling square, mass square. You are right, completely right. But here is rigorously. This is rigorous in the sense that, oh, I know this coupling is equal to this thing. Okay, okay, and this is the information on shell. You see, because the problem is with what you're thinking that is correct is that you kind of guess what is the amplitude of shell, but we don't know. Really, we don't know. Okay, and here. The coupling here is on shell. Is the coupling on shell?
Right.
Okay.
Right. Okay. Thanks.
Now the point here is that there are more information. I'm going to very slowly. There is more information thanks to crossing. Okay, because there is crossing. You can see here when I look here that the G31 appear here and appear here. Okay, in different dispersion relation for k equal 1 equal 2. So it means that I can derive it for relating it with this coefficient, the sum over this coefficient, or I can relate it with sum with this coefficient. Okay, so what is telling me here is I have the system is over constrained. That's great. It means I have a lot of constraints. Okay, deriving by looking at this thing. Okay, so this has to be equal. So it means that this sum over this thing has to be the sum equal to the sum over this thing. Okay, And this means that, and I have many of them. I can go k1, 2, 3, 5 to infinity, and I have dot, dot, dot here because it's an expansion in S. So you see a lot of information is there that never has been considered before in this case, okay? And now that's the full thing, okay? Let me take full thing, okay? Because I have infinite constraints. I have infinite particles, yes, but I have also infinite constraints, okay, in the spectrum and in the couplings, okay? In particular, this one, okay, relating these two thing that I'm saying, disappear because of crossing, okay? Relating this sum over here with this sum over here, because this is what this guy is the same, is giving me this constraint, okay? So you see a kind of constraint that appear. Okay, the sum over all particles of the coupling square or mass square times depending this number that depends on the spin of the state must be 0. Okay, so this constraint for all particles mediating the pion amplitude, except for scalars. If it's mediated by a scalar, you see if the spin is 0, this goes to 0. So that's the interesting thing. A scalar never appears in these constraints. Okay, so mediating spin 0 states never are kind of decoupled, but the other spin are related. Okay, so you have a particle with some spin larger than 0, it will come here, and we have to satisfy this constraint. This is 1 out of infinite. Okay, this is the point. Okay, and I was saying, I was asked before, there are more dispersion relations. Yes, indeed, but can be shown that only taking now this was fixed, this amplitude a fixed u, taking a fixed t, this 2 is enough. And the rest are dependent, okay? So let me look at this implication of taking this, all of them, all these constraints, okay? All the constraints. Now why there is today you can do this is because there are numerical techniques that we use, okay? This is the nice thing of the Bootstrap program. People have been programming things that where you can put all these constraints and get in an easy way in the computer, and you get information. Okay, and we are using kind of the software that people develop. Okay, this is the key point. Today probably was not in the previous years when people were already knowing that there are these dispersion relations to get information on things. Okay, and now let me assume here that m over s. Okay, I can use k equal 1. Okay, m over s at infinite, s modulus s goes to infinity. This goes to 0. This is not. This is a little bit more than the Froissart bound, okay? And there's some argument I don't want to enter here because I'm also not an expert, blah, 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 but you can read in the literature that, okay, that is something you could expect in the large n for pions, okay? So I'm using here, but there is motivation, but I don't want to enter into this motivation. Let me take it with some motivation, okay? So let me see the implication of this thing, okay? If you don't like k equal 1, okay, you have to throw this first line and go with the other. So still you have k2, 3, you have infinite there. Okay, so with you don't put k equal 1, you miss one of these relations. Okay, well, infinite of them because this is an infinite expansion. Okay. Okay, so I'm taking this. Okay, so I'm taking this k equal 1 line, and let me see at the implication. In particular, I want to say something analytical, and after that, I'll put the full thing and the constraints you get. Okay. Because it's a lot of information already by looking at these constraints, okay? This one, the one I was showing to you. And now it has the interesting property that this coefficient here is negative only for spin 1. If you go here and you put spin 1, this value here is negative. If you put a spin 2, it's 0, particular, but you put a spin 3, 4, 5, 6, this coefficient becomes positive and growing with the spin, okay? Okay, grow with the spin with, you see, 1, 2, 3, 4 powers, okay? 4 powers of the spin. So as soon as the spin grows, the number becomes larger and larger. So I have a relation that on one side, the spin 1 is negative. I can put it on the other side, the spin 1 equal to the contribution from the other spins. By some accident, the spin 2 disappears. So the first is 3, 4, 5, 6, with a coefficient in front that is growing, growing, growing. Okay, and this has to be satisfied by the spectrum of the theory. This is an implication of this constraint. And tell me something important, that spin 1 must be in your spectrum of your theory. Okay, this is a theorem. If there is no spin 1 particles, it means this is 0. You have positive quantities here that has to be 0, that the only solution will be that the couplings are 0, everybody is 0. Okay, free theory. Okay, so if, of course, this is a solution, everything is 0, nothing, okay, of course. But if I want to in a non-trivial interacting theory, okay, the coupling goes to 0, but it's not 0. Okay, remember, the large n tells you the coupling goes to 0, but you don't want to take exactly n infinity, but approaching, okay, that formally approaching that limit. So I want to get information. So it means that the spin 1 must be there in the spectrum, okay? And with the largest, second thing important, very important, the largest coupling to pions, because you see the higher the spin, the factor in front is larger, okay? So in order the spin 1 so the spin 1 had to handle with all of guys here, have to compensate, okay? The other guys contribute to the sum here. And because the coefficient is growing with growing, if we want to, this coupling must be also, if this coupling a higher spin is large, it will mean that this has a large contribution. So the only way I can handle to be true is to taking the coupling of the pion of the spin 1 to be very large, okay? So from here, you see that the better, if you want to satisfy that, the coupling for the higher spin goes to 0, okay? Or if you want, goes to 0 as relative to the spin 1, okay, in order this to satisfy, okay?
I guess
So
you're making an assumption. Sorry, I think you're making an assumption that the mass of the higher spin state does not grow. The mass of those states does not grow as faster as the coefficient grows as function of J.
No, I'm not taking an assumption. You are right. It could be that the mass of the higher spin grows, okay, very much, okay, and compensate this factor here. It could be, and the coupling don't go to 0. Yeah, sorry, you will say, yeah, it could be this like this, okay, but. I'll discuss about this a little bit when the mass doesn't grow. Theories where the mass doesn't grow. Okay, I'll come back to this point. You're right. Thanks. Okay, it can be. You see, here I don't get much information. I get a flavor. I'm putting this because it's analytical formula. I have infinite of them, but this analytic formula I can see a flavor of the importance of a spin 1 here. Okay, the spin 1 here has to compete with all of the guys. Okay, so this is telling me that this is the most important guy here. Okay, that the coupling clearly must be large, or if you want, yes, probably have to say the coupling normalized to the mass. Okay, probably something like this. Okay, you see, yeah, you are right. Thanks for
thanks
for this point. Okay.
So I have another question. So you have like a lot of over constraint, right? And that constraint the same set of the coupling, like a pi G pi I. So can you pick like one of the strongest one?
Sorry.
So from the previous slide, so you have a lot of over constraint conditions, right?
Yes. Indeed, I'll come back to this point. Yes.
And those are the function of the same coupling G pi I. So is there any like a strongest constraint that you can only use instead of using all of them?
No. Yeah. This is a very good question. We try. We have done some part of it in the paper. We look at instead of going to the numerics, okay, let me think. Okay, yeah, I have a lot of them, but some of them must be more important than the others. True. We explained that you can get something analytically. That's true. Okay, but of course I will not elaborate here. I'll tell you a little bit how the analytic is a fascinating thing that goes into some mathematics that we didn't know. By looking at the important ones, okay? I'll tell you a little bit later. Okay. But indeed, it's not so easy. Yeah. Indeed, it's not so easy because you have infinite particles. Okay, so the sum is infinite. Okay, it's true that you feel it. Oh, these are very more important. Okay, so yes, there's a feeling, but at the end of the day, okay, we have to put all of them, and we were not able to say. We spent time on this thing, but we were not able to say, oh, with this one you get most of it or thing like that. Okay, good question. Anyway, the point here is that when we put in this thing, because already gave me a flavor. Spin 1 is important and bring me something in the old days was called vector meson dominance, that it was assumed to explain QCD experimental data. Okay, the idea of that if you look at pion scattering mediated by the spin 1 state or other contribution to some other processes in low energy QCD, if you were mediating this state, this amplitude or this observable by the rho, you were getting roughly means I don't know 20%, 30%. The agreement with the data. Okay, so there was an assumption. You say, oh, this is mediated only by the rho. I know there are many particles, okay, in QCD, many resonance in QCD, but if I put only the rho, I get agreement. Now, this is a kind of first to me idea of why the thing was working. Okay, so this was just one empirical evidence. There was empirical evidence of this vector meson dominant. This is kind of more mathematical evidence that this should be like this, becoming of these constraints. Okay, and I'll talk later much better, because of course here I'm putting one, but there are many of them, and it will tell me this. In fact, let me go probably to this thing, because I'm going very slowly. Okay, so yes, I have to put all constraints. There are many of them. They write like this: some over things related with the spin or of wherever equal to 0. Let me skip them and let me get two numbers. Okay, I'm saying this evidence that the coupling of this thing must be larger. You can make it. You can get to numerical values. Okay, and this is the numerical values. Okay, so if I look at the coupling square of the different spins, okay, I have to normalize it, okay, and normalize to the mass square over f pi square. F pi is because f pi square is related with the G10, the first coefficient of the expansion of the amplitude. I see this numerically comes up to be the case, okay? So the coupling of spin 1, this is the bound, okay? It must be smaller for the spin 1, something 0.78, for the spin 2, 0.12, spin 3, 0.03. So you see really here now, these are numbers coming out. Okay, the higher the J, the smaller coupling has to have, because coupling is square to the pion. Okay, so this you can get a strict bound. Okay, and of course this more or less follow QCD, as I was saying, that the rho seems to be dominant, and if you do these numbers we were showing for spin 2, you get the number. This is QCD now. This is a bound, upper bound. Okay, it has to, yes, upper bound. The coupling mass square has to be smaller than this. And this is the number. So in the case of rho, is a little bit smaller than this. That is spin 1, spin 2. That is F2. The coupling seems to be saturating this bound. Okay. Again, of course, QCD is not infinite number of colors, but these numbers are not far away from these things. Now let me go to the second part, okay, because I'm lacking time, and bounds on now the Wilson coefficients. Okay. So if the couplings are bounded, now it's obvious. If I go back, these formulas, it is bounds. Okay, some over infinity, but I see that the bounds are becoming smaller and smaller as I increase the spin of the state. So it's clear I'm going to get a bound here on these coefficients. Okay, and this was discussed long ago for many theories. Okay, I'm discussing for this particular theory. It has been a lot of discussion of different theories, this graviton scattering, scalar scattering, this thing. That when you look at as I was saying, the amplitudes, in the amplitude, these G's, this coefficient G to 0, G to 1, are related with the chiral Lagrangian. And here I give you the exact relation with the chiral Lagrangian. This is the chiral Lagrangian of QCD with the Wilson coefficient L1, L2, L3, L4. Okay, and now you see these G's, I call it tilde because this is normalized to what they call G10. I'm going to take a ratio of Wilson coefficients because this is what they think is going to be bounded. Okay, of course, the absolute value goes to 0 in the large n, so it's ratios that are going to be bounded. And I'm going to look here is only these two Wilson coefficients that are related with, this coefficients that appears in my amplitude when I take the limit of energy is going to 0, that are related with the Wilson coefficient of the chiral Lagrangian in this way, okay? Here, M is the mass of the first resonance. Okay.
Hello?
Yes.
One question about, so for the chiral Lagrangian, you also work in the leading order in large NC limit, I guess.
Yes.
And then L2, I think it has a double trace, so it is sub-leading in one of NC compared to other single trace operators, no?
Yeah, you are right. You're completely right. Thanks. Yes, a priori, a large chain, you can say that the single trace operators are the leading one. This you cannot throw them away because, this is a problematic basis that people use in chiral Lagrangian. As you know, these two double trace can be related with a single trace. Okay, so there is in some sense in large chain there is a relation between L1 and L2 that I forgot. L1 has to be
L1 term 2 trace scale. Yeah,
exactly.
Okay.
Exactly, because this double trace, you cannot throw them because there is another single trace operator, and because of people like it to write it like way, you throw away you write the single trace as a double trace, but there is another one that. at the end of the day, what is telling me here, right, that in large N, L1, L2 is but I put it here, sorry, too,
Okay,
because
thank you.
probably people are more familiar with this way. Okay. So now there are bounds, and now the first thing you see is that the bounds, okay, these coefficients that parametrically goes are order 1, so they go, the ratio are order 1, so go from 0 to 10, okay? So in the big plane, you will say this, if I do naive estimate, I would say, oh, this coefficient, or the ratio of coefficients, okay, because I'm divided by pi square, m square over phi square, this coefficient, this Wilson coefficients occupy between 0 and 10, I don't know much, you see that occupy a small region of this parameter space, okay? The allowed region is this thing, okay, and this is bounded from, for example, this G to 0, from 0 to 1, and this one is a little bit more complicated, and I want to discuss a little bit this, okay? This is the allowed region comes in, and it looks like a polyhedron, okay? So it is a kind of polyhedronal bounds, and this is what people already realized years ago when they started this news a few years ago, because started this business of doing this thing that, looks like effective field theories look like effective field theory hadron, in the sense of all Wilson coefficients that you thought these are order 10, order 1 parameters. No, they are like living inside these polyhedron shapes. Okay. Now let me tell you a little bit more, because there is more information in this allowed region that I want to go probably fast. Okay. The first thing is talking about the scalars. If you look at the scalar contribution, as I said, they don't enter into these constraints. There's a couple, and because but the physics of this scalar is very simple. This is like you always live in this line, scalars. One single scalar will always give you here the contribution here, and this is kind of the Higgs UV completion. Okay, I can have pion UV completed by only scalars. Okay, and that's, we know, is the Higgs mechanism. It's a possible UV completion that lives here. Okay, sometimes we want to also learn about different UV completion. This could be the famous one, but I'm more interested in higher spin UV completion. Okay, and now you go to higher spin UV completion, you live in this blue area. Okay, so the spin 0 here, but if you want to have it, you see very highly constrained, living in this almost small strip. Okay, and of course I was showing this is allowed because in a theory where you have a scalar, you can have combination of scalar and higher spin. You can live in this convex hole that they occupy all these things. But you see, when you specify the theory, you see that spin 0 live here, higher spin live here, very, very in a small region. Of course, you combine the two things, the space becomes larger. Okay, and I want to talk about a little bit here because it's difficult. There is easy to see that there is a straight line here, this straight line here up to some point, and after that, this is a curved line that you have to get numerically. This is why the different approximations are difficult. Okay, numerically, the exact bound here has to be numerical, and it's a kind of a difficult thing. But I want to say a couple of things. First, there is the kinks. Okay, this bound has two kinks. One is here. Okay, just a straight line all the way here. And what is the theory in the kink? Always there are important theories at the kinks of this. There is this polyhedral thing at the kink of this polyhedron. There are interesting simple theories. Okay, in this case there is the vector theory. There's a spin 1 theory. Okay, this is a theory with only one spin state. Okay, and it's very interesting. This is why I was saying, okay, can you do something analytical? Yes, sorry, I only give you a grasp of the idea that if you do it, you will see that this, to prove that this is a spin 1 theory, we had to prove something mathematically. Okay, going to this analytic expression that the determinant of this Hankel matrix that looks infinity had to be 0. Okay, so sorry to do this is just a mathematical open a parenthesis on the how things get into when you do analytical things. Okay, otherwise you have to do it numerical. On the other side, I have a very simple theory that is what is called SU model, where only have is a theory where only one mass. Okay, it's a higher spin theory with all particles spin 1, 2, 3, 4, 5 equal mass m. It has very simple theories. And in fact, in the theory, you can see that they calculate the couplings. Okay, this is where you maximize the effect of the higher spin. Okay, you want to, and this is the theory. You want to calculate, maximize the effect of higher spin to go to the corner of this thing. Okay, because spin 1 is here. Okay, and higher spin can go. I mean, other spin contribution can go here, and this is the way to maximize. And now there are other interesting theories. Okay, these are possible theories, but also more interesting. For example, we know in string theory You can have UV completion coming from the Venetiano amplitude, or in this case, it's called the Lovelace-Shapiro amplitude. Okay, and now it's interesting to see where it resides in this particular amplitude, where it resides in this plane, and looks like you are very close to the bound. Okay, remember this bound is very difficult to get. You have to get it numerically, and now only this is an approximation. What I'm showing here is that as soon as I increase my numerical thing, I can get more closer to this red line. Okay, but I numerically never got to this red line. This red line, in fact, is just extrapolation between this vector theory and the other theory. Okay, but numerically, I'm expecting to be getting closer and closer, but I don't know how close. Okay, so there's a numerical thing I can only tell you here, and I can see that this theory, the famous theory coming from string theory, resides very close to this boundary. Okay, but I don't know exactly. So it's not exactly on this red line that extrapolate between this and this, but I'm not sure. If look like it could be on the boundary of this, the true boundary of this thing. Okay, so this thing is still unknown because numerically I have to put all the constraints, and this is a difficult thing. Okay, and analytically we are not able to prove it. Okay, anyway, there is a interesting theory that resides, seems to be on the corner. Now
But here you said the kink only appears for the spin on a vector, single vector.
Exactly, the king. Okay, so there is the king appear here. There's a king here, and of course at the origin. Yeah, and the theory here we were able to prove by proving this thing, this mathematical proof that the terminal of this thing is zero. That only reside. Here Rastelli was claiming probably this could be the large N QCD lives in this king knot. What we show is that what it lives here is the theory of a spin one state, a theory of a single spin one state, okay, with all higher spin at infinity. There's a limit where all higher spin are at infinity. Yeah.
That's great. It looks great. Okay, thanks.
Yeah.
Sorry, I'm confused a little bit then. So according to the sum rule that you showed earlier, I thought that the exact vector meson dominance is impossible. So whenever you have a spin, but then this theory seems like.
Yeah, sorry. Yeah, you are right. Okay, so this is what we're saying here. It's spin one, but also all the state at infinity, giving you a contribution. Exactly. Those guys, you can take this limited formal limit at infinity, all the masses. Yeah, it's a tricky thing. Thanks for one more details have to give them. You are right here. You will say impossible because spin 1 0 cannot exist. You have 1 equal something so equal to 0. Okay, impossible. Right.
Yeah.
But you can move these masses to infinity in a way that these constraints are satisfied. You are right.
Okay, I see.
Okay, and this is what the difficult thing to test. Okay, so when I'm saying this thing, okay, so this is a formal limit where I can send this thing. All constraints are satisfied. But if you look at the Wilson coefficient, is dominated by this guy. Okay, this is dominated by this guy. But this, yeah, you are right. Okay, I can send it infinity in a very peculiar way. So this is why it was difficult to test that this is a spin one theory. I should say that the only guy that remains at finite value, the mass of the state that remains at finite value, the others send to infinity. Thanks.
Yes. Okay. Thank you. Understood. Thanks.
Now, let me flash a little bit. You can do better if you assume, for example, that the spin one is the lightest. That's happening in QCD, and the other a little bit heavier, not much heavier, like 1.65. Okay, it's happening in QCD. Now the area starts shrinking. Okay, become really this green area. And if you impose more things like, I say like in QCD again, that the rho meson spin one exists and it has a non-zero coupling to pions, okay, and I fix this coupling to be not very large, like 0.33, normalized in a peculiar way, I get the smaller and smaller regions, okay? So you really get into the as soon as you put that the spin one exists, and some assumption, you really see that the Wilson coefficient, I don't have much freedom into it, okay? And now, like I was saying, even you can compare with QCD, with lattice results, okay, that there are few of them at large n. Okay, infinite n is very difficult, of course, I understand, because you have to extrapolate at the large n. But this is this purple area here that they were not showing many, they were constraining this area. What we know now, we can show them. It would be good now. I was trying to contact these people because it is clear you can have to combine this positive bound with lattice result, because the lattice result put you into this area, purple area, but most of this area is excluded by the positivity constraint. So if you are trying to look at areas that you know they are not physical. Okay, now by comparison, of course, although I'm just flashing here the experimental data. Of course, I must to say that this is data coming from some analysis, and there are other analyses that show data down here, so not such a nice agreement with this thing. Okay. I want to flash. There are many other things, but I'll flash only one simple thing. I want to say something that this helps to something that was surprising to me, because I spent time on this, as Minong was saying before in my presentation. I spent a lot of time to understanding holographic QCD, because it's a surprising theory of where you do a 5D model of QCD mesons. And let me tell you only that it was amazing, because we were agreement, a very nicely agreement up to 10%, like almost a 10% agreement with many experimental data of QCD. And it was surprising why this thing works so well, okay? Because this is a theory where you only put the spin zeros and spin 1 state. You put infinite of them, but you have only spin 1, 0. Now this positive constraint explaining why this success. We see that the higher spin are restricted, spin 1 dominates, okay? So it could be that, okay, this is the reason, okay? If you have a theory where you mainly put spin 0 and spin 1, you're going to catch most of it, okay? And this could be explaining why holographic QCD is a nice way of trying to approach QCD, even that only deals with 0, spin 1, and not the spin 2, 3, 4, 5, okay? Okay, so let me probably wrap up, because I only want to say that it could have impact for LHC physics if you're interested in BSMS scenarios, because this tells you a little bit a relation between indirect effects and direct effects, okay? Because indirect effects is coming from what you call the chiral effective field theory, okay? And direct effects is coming from producing the particles, okay? So in some sense, we'll learn a little bit what is the impact of, you see, usually we put a spin 1 state to when we do these studies, but of course now we see that there can be higher spin state, and you can estimate how big it is, this contribution of higher spin. And in particular, for example, in theories of composite Higgs, we can say that, for example, the contribution of higher spin can be at least 20% more than considered, and can change a little bit the indirect bounds when you relate the indirect bounds with direct bounds. Okay, let me a little bit skip these things. These details, okay, but you're interested, there is things to say on the large N now when you go to other scenarios, BSM, like composite Higgs, okay. Now, if you can say, if you don't like M over S going to 0, and you think, I have to take the Frost-Air bound MS squared, there is an analysis very similar, but the only thing is that there is a difference between what is in the king you find the spin 2 state instead of the spin 1, okay. There is some thing that you can also do there, okay, but I'll skip it because I think I'm out of time, okay. So let me move to the conclusion, and I'll be happy to answer any questions. So my point here is to say, positivity constraints, positivity bounds that come from crossing analyticity and intrinsicity show these features of EFT hadron, okay, structure of the chiral Lagrangian, okay, the Wilson coefficients lives in small areas, okay, that polyhedral shape, okay, and I think it's a nice thing to allow to get information of this large chain theory. And what we are more interested, kind of what that could be, how it looks like UV completion of a theory of Goldstones, okay, and I didn't spend this time to say, because okay, skip it. You can prove, for example, that all J's are needed, okay? I said the spin 1, but you can go with this thing by looking at the constraint, and you can prove that also spin 2 is needed, the spin 3, spin 4, okay? So you can prove that all J's are needed, okay? I skipped this information, sorry. Anyway, the thing you get is this vector kind of meson dominant. Higher spin has to be always smaller than spin 1. And probably this gives an explanation of vector meson dominance or the success of holographic QCD. And of course, this is done for pion scattering, and but kind of straightforwardly, of course, straightforwardly in big quotation marks, because it takes time to do this analysis. You can go it for other amplitudes and I don't know, pion with photons, something like that. We are doing scattering of photon and pions, getting to the anomaly thing and things like that, and get extra information. Or also could be probably interesting to go to dark matter, where you have candidates of dark matter where are strongly interacting state, and say something, and Okay, well, I stop here. Okay, thank you very much.